All right, now we're going to look at integration by parts. We've actually looked at this earlier. We've done derivatives by parts. If you think about it, is if we had a function that looked like this, this has two parts. This is the f part, and this is the g part. So if we're going to look at the derivative of this, and this, the f and g, see, f is x, and the g is cosine. So the derivatives of both of those, derivative of x is 1, derivative of cosine is negative sine. Since we're multiplying, we're making it bigger, so it's a plus. It's going to be cosine from cosine going around like this. So it's cosine x times 1 plus x times negative sine of x, which becomes cosine of x minus x sine of x. So basically, the product, the differentiation rule, if we had f and g, the derivative would be g times f prime plus f times g prime. That's what we're going to look at here. Now we're going to look at, these are the parts we're looking at. That's why it says integration by parts. Now we're going to look backwards. What we start off with is this function, but we're integrated by two parts. We have u of x and v prime of x. Actually, I should, yeah, oh well. How do we differentiate which one's which? In whenever we're just given an example, how do you know? Well, the u function, this can be the derivatives differentiated till it becomes 0. In other words, it's finite, like x squared. First derivative is 2x. Next derivative is 2. Next derivative is 0. So if you're given an option, look for one that's differentiable till it goes down to 0. The v prime will be one where never goes to 0. It keeps on repeating itself, like the cosine. Derivative of cosine is negative sine is negative cosine, and so on and so forth. All right, so you could integrate this one forever. And this one you could differentiate that till it becomes 0. So integrate infinitely many times. All right, so let's look what's happening here. So if we look at what we have here, the u of x times v of x. Oop, that one's there already. So this is a product. We've already seen this. We do that. So this is the f and g. So this would be the derivative of the first one, which is u prime x times v of x plus u times the derivative of the second, which is what we set up earlier, but this is, we're not going to use u and v's. That's the differentiation rule. Now, when we go to integrals, we're going to go backwards. We're going to look at the integral of d dx ux vx Now we're going to integrate each of these parts. And we're going to integrate the u prime x v of x plus u of x v prime of x dx. All right, and if we simplify this, we have the derivative, the integral of the derivative of ux vx with respect to x. We can now distribute both of those. We have the integral of u prime of x vx dx plus the integral of u of x v prime of x dx. All right, so all we did was we're now just setting it up because it won't stay this way. Case in point. What's the integral of d? This is the derivative. The integral of the derivative is simply the function itself. So, and then we have like here's these are partly integrals, part just regular functions. All right, so this becomes u of x v of x, and these remain as they are for right now. U prime of x v of x dx. Now, this is where we are right now. Remember what we're trying to integrate. We're trying to integrate u v prime. So we have to solve for this equation. So this one goes over there. Again, the most difficult part about this is determining which one's going to be u, which one's going to be v. All right, so we have this side by itself equals this minus that. Get to the top of the page. Yeah. So the integral of u of x v prime of x dx is equal to u of x v of x minus the integral of u prime of x v of x dx. All right, so since we know these are all values of x, we can make it look smaller. So it's u v equals, the integral of uv equals uv minus the integral of v du. Now this is dv, this is derivative. All right, so this is the formula we'll be using. In other words, once I give you, well, let's look at the example. Once I give you a function, you have to determine what part is u, what part is v. The example one says x cosine of x dx. Remember the conditions, so we're trying to find. We have u prime, v prime. So the u part is the one that when you take derivatives, it becomes eventually zero. The v prime part is when we integrate it, it goes on forever and ever. So the u will be the x, and the v prime will be the cosine x. U v prime. Okay, we'll be using that this formula to solve this one. So just fill in the rest of the blanks then. The derivative of x is 1. The integral of cosine is sine. So we have our integral of cosine x dx is equal to, get that formula, u times v. So it's x sine of x minus the integral v du. So it's sine x du is 1. X sine of x, and the integral of sine is negative cosine plus some constant, since it's an indefinite integral. So this becomes x sine x so that is what our integral becomes. And so yeah, it all depends on how you choose u and v. If you choose it incorrectly, then I mean, if we chose the integral to be x, then we go on. Both of them will go on forever. None of them would ever terminate. So there's some other example. Example 2. Example 2. Integral of ln x dx. Remember, we want to use the formula we just e equals u v minus v du. That's the formula we want to use. So the first thing we have to do is define u. And v prime. Well, the v prime, there's an invisible, there has to be two parts, the u and v. This one's going to be 1. So this other one's going to be ln x. Because we have to have the u and v part. So what we have here is this. Well, let's find u prime. The derivative of ln x is 1 over x. The integral of 1 is x. So we fill this up. So the integral of ln x dv, which is 1, u of v, so it's x ln x minus the integral of v du. X du is 1 over x. So x ln x, the x's cancel, so the integral of 1 is just x. So there's our integral. There's our answer. Let's look at example 3. It's pretty much straightforward. It's once you locate the u and v, it makes it our u v prime, I should say. Okay, so let's look at this integral of x squared EX DX. So the only one that has, if we take the derivatives, come out to be 0, would be x squared. So u will have to be x squared. So du would be 2x. That means v prime will have to be e to the x, because I can integrate that forever and never get 0. So that's an important condition I have there. So we have everything we need. Let's plug in what we have. So we have our function, which is x squared e to the x dx, uv, which is x squared e to the x minus v e to the x du 2x dx. So x squared e to the x dx equals x squared e to the x. Okay, so what we look at here, this one looks similar to this. And we can't do that one, so we got to do it again. Since this is not integrable yet, redo the process again for this part. For this part here, we have u prime v prime. So we have x is my u, ex. So the derivative of that's 1 and ex. So this part, we have the integral of x ex dx becomes uv, which is x ex minus the integral of v times u prime, which is 1. That becomes ex e to the x.
Professor,
Yes.
but I'm a little bit confused. What happened to the x squared?
Oh, because we got to this point here, okay,
Mhm.
we start off with this, we got to this part here. We have to take this integral first. Well, we can't take this integral first because it's not in an easy, simple form. We can't integrate this. So we have to do it again by parts. So right now, all we're doing here is this part right here. That's all we're
Okay.
doing. Because yeah, then we'll incorporate everything. It's just that we may have to do it a couple of times. But remember the condition was of u, it had to be derivatable or differentiable till it becomes 0. And this is the reason why. Because if we take the process starts at x squared, brings us down to x, well, we have to
Mhm.
redo it. And that's the whole reason we can't, after this one, we don't have to go any further because it disappears.
Oh,
See,
okay.
so
We're taking it
yeah,
separately and then we
we're
put
doing it
it back.
separate.
Okay.
Yes, yes. So right
Okay.
now, we're just doing this part down here.
Oh, okay. Thank you.
I'm sorry, yeah, I'm sorry, yeah, but yeah, great question. Okay, so now we have an integral of e to the x. Well, the integral of e to the x is simply e to the x. Since it's an indefinite integral, it's plus c. So this takes place of that. Okay, so our original equation, let me go to the next page so I have more room. So our original equation, which was x squared e dx, we broke it down to x squared e to the x minus, we had the 2 out in front. And that became e to the x squared e to the x minus 2. This whole integral is what we just calculated here, which is ex minus ex. So it's ex minus ex plus c. So we have x squared e to the x, distribute that 2, so we have negative 2x e to the x plus 2 e to the x. Negative 2c is still going to be a plus c. So that's our answer. This is our answer. Because, yeah, it's, a lot of people ask us, when I distribute that, I get negative 2c. That's still a plus c, whatever that is. All right, so we have to worry about putting a minus c. So we just keep on going that if this one still didn't become an integrable one, then we'd redo it. Like in case the next example. Example 4. E to the x. So integration by parts is whenever we have, because we don't have a chain rule type rule for integration. We have a chain rule for derivatives, which gets us to this problem. When we go backwards, we have to do it by parts. So the first thing we have to do is label our variables. Now, if you notice these, both of these go on forever and ever and ever. So let's label these as, would it matter? We'll find out in a minute. So if e to the x was my u, then my du would be e to the x. The integral of cosine is sine. So we have our equation ex cosine x dx equals uv, which is e to the x sine x minus the integral of u v prime u, which is cosine ex, so it's ex cosine x dx. Okay. Cosine times sine. That's what it is. It becomes, this is sine. That's where I messed up. This is the integral of v du. Or no, not v du. Yeah. So sine ex. All right, so ex sine x minus, we have to integrate this one. Well, that's also by parts. So u is ex, u prime is ex, v prime is sine x, integral of sine x is negative cosine x. So we have to do it by parts again because of this one. So we have uv, so it's negative ex cosine x minus the integral of v, which is negative cosine x, du, which is e to the x dx. That's this whole part right here. So we have ex sine x plus ex cosine x minus, so that's a becomes plus and that becomes minus, so it's minus integral of ex cosine x dx. Does this one look familiar? Yeah, so now what we look at, because we know this side equals ex cosine x dx. You notice this side and this side look equal. So I move it over. I combine them. Because both e of x and cosine x never run out of integrals or derivatives, they'll eventually get to a point where they look identical. So that cancels. So we have here 2 integral of ex cosine x is equal to ex sine x plus ex cosine x. Let's see, because we took the integral of this one. This should give us plus c from that. Since we were looking for this part, so we divide both sides by 2. So we have our solution. The integral of ex cosine x dx is equal to ex sine x plus ex cosine x over 2 plus c. Because we can't, I mean, this part repeated itself, so we combined it, and we're asked to solve for this side. And that's our solution. Okay, so we looked at so far, where it's definitive that we have a u and a v prime. The v primes could be integrated forever, and the u aspect can be differentiated a finite number of times. We also looked at one where if it's missing, if a term is missing, then it's a one, and we can integrate with that one with the dv, the derivative, the v prime part is one. So when we integrate it, it becomes x. And again, integrate it again, it becomes x squared. So that's the hard part. Then we get to these last two examples. This is where we have to repeat the process multiple times until we do get rid of the integral. Or if it keeps on repeating, we keep on repeating itself until the part, our question part, is repeated somewhere in the solution. Then combine like terms and solve. The next example, what if we had an exponent in our function? What if we had that? So what's this going to be? Because remember, we still have to come up with our u prime, v prime. We have to remember this. No. Cosine of any power n can be broken down into two parts. Cosine n minus 1 times cosine x. We could break it down to our u and a v parts. So the u part would be the cosine n minus 1, and the v part is our cosine. So we're making one of them definitive because we're losing n's each time we take a derivative of it. It becomes n minus 1, n minus 2, eventually n minus n. However, the integrals of cosine keep on repeating forever. Now, the derivative of cosine n minus 1 x. This is where it gets complicated because the derivative, it's a chain rule. We'll take the derivative is n minus 1 cosine n minus 1 minus 1, which is n minus 2, times the derivative of the inside. So to derivative of the outside, now we take times the derivative of cosine. The derivative of cosine is negative sine. So that's the derivative. That's this part. Derivative outside times derivative of the inside. And the integral of cosine would be sine x. Okay, now we're going to plug everything in there. So it's integral dv equals uv minus integral of v du. That's our formula. So we have originally cosine nx dx, u and v, which we calculated. It's cosine n minus 1 x times v, which is sine x, minus the integral of sine x times n-1 cosine n-2x times negative sine x. He's in there. B sine x and then n. That's this. Okay. So we have cosine x n-1 times sine x. What can this negative sign and that change? So it becomes a plus. The n-1 can come out in front. So we have sine x times sine x is sine squared x cosine n-2x dx. Let's see what we have now. Cosine n-1x sine x n-1. Now we have sine and cosines. It makes it much easier if we convert this to 1 minus cosine squared x, because that way it'll give us nothing but cosine terms. Cosine n-1x times sine x plus n-1. Now inside here, I could distribute. So I have cosine n-2x minus cosine 2 plus n-2x dx. I distribute. Look at both of these separately now. The integral of cosine n-2x dx minus the integral 2 minus 2 cancels cosine n brackets. So we have cosine n-1x times sine x. So it's n-1 integral of cosine n-2x dx minus n-1 integral of cosine nx dx. So we see on this part, looks like we started off, it equals the left side. So if we add both sides, this cosine n of x dx plus n minus 1 integral of cosine n x dx equals all this stuff. Cosine n minus 1x sine x plus n minus 1 cosine n minus 2x dx. Holy smokes. So we have a 1 here. So we have 1 plus n minus 1 integral of cosine n x dx. The ones cancel, so we just have n plus this whole monstrosity. N minus 1 cosine n minus 2 x dx. Divide both sides by n. Ooh. So that gives us just the integral of cosine, which we're looking for, cosine. The left side will just have integral of cosine of n of x dx equals cosine n minus 1x times sine x over n plus n minus 1 over n, the integral of cosine n minus 2x dx. As far as we can go, because we'll keep on repeating the process over and over and over and getting and bigger, bigger, and bigger. Now, what we did here, notice, we took an exponent, n, and you notice here, all of these are smaller, n minus 1, n minus 2. That's called the reduction formula. So it takes the integral of some power and leaves it at a lower power. In other words, what would happen is it'll keep on getting smaller and smaller and smaller. We would keep on losing one each time. So for example, the integral of cosine 3x dx. After that, we'll just use this formula here. So our n is 3. This is cosine to the power n. So we have is cosine 3 minus 1x sine x over 3 plus 3 minus 1 over 3 of cosine 3 minus 2 x dx. Anywhere you see an n, I put a 3 in its place. Cosine 2x times sine x over 3 3 minus 1 is 2/3. The integral of cosine x dx. So we have the cosine squared of x times the sine of x over 3 plus 2/3. Integral of cosine is sine x plus c, and there's our solution. That's how the reduction formula will work. Right, so that's what we're doing so far with indefinite integrals. Can we do it with definite integrals? Yes. Because once we get to this part, instead of having a plus c, we will have actual values. So,
Real fast. Do you
yes,
know what's the end of the page before the one you just finished? I didn't catch the end of formula you read. I think I got to.
this one here,
Yeah, that big mess there at the
that,
bottom.
yeah.
Okay, just want to make sure I wrote that all in right.
Yeah, this is the left side of the equal sign. This is the right-hand side. I just combined these two, so I have 1 plus n minus 1. They both have radical cosine n to the power x. Cosine power n of x.
Okay, yeah, okay, I got you.
And this is the u v integral of v u prime. Or yeah.
Okay.
Yeah, I do apologize, but it cleans up pretty well when we have real numbers. It cleans up really well.
Yeah. So with this reduction formula, we can essentially plug these into that, right? Instead of having to go through all of that.
Right. If we're like this example here, this is given cosine of n. Once you have n defined,
Mhm.
I was going to go through and redo the whole thing. Said no, we don't have to. It's right there. Anytime you have an integral of cosine to whatever power, just
Mhm.
plug in n and go from there.
Okay, cool. Okay, awesome.
Right.
Thank you, sir.
You're welcome. So now let's look at an example of definite integrals. This is example 6. So we're going from a to b. U of x v prime of x dx is equal to u of x v of x. But this is from a to b. Remember, that was minus the integral of a to b v of x u prime of x dx. That's our formula. This is our formula we'll be using. Notice it's the same formula, except now we have bounds. So this one says find the area of the region bounded by y equals x e to the power x. And the x axis from x equals 0 to x equals 4. The question here, the question gave us, the statement gave us everything we need. How do we know we have to use integration by parts? What in there tells us we have to use integration by parts? Anybody?
Is it how the equation is laid out, like x to the power of e negative x? So you can split them, x being 1, e
Well,
negative x.
why aren't we taking derivatives? First off, it tells us area of the region bounded by. Yes, it does have a lot have to do with this, but first off, we know we're doing integration, but we're looking for the area. Remember, integrals look for area between two bounds. So that's the first thing that tells us integration. Because we have a u times v, that tells us we have to use the integration by parts from a to b. Yeah, so all these things are now piling up inside there. So what do we have? We have our integral from 0 to 4 of our equation. We have the formula up here. We just have to figure out what's the difference between u prime, v, and v prime. So let's look at those. So which one of these would be the u, which one would be the v?
U is X.
Yes, why?
Oh, because it can go to 0.
Very good, because the next derivative would be 1. Yes. So that means v prime would have to be e to the power negative x, because the integral of that will just keep on going from positive, negative, e to the power x. So the derivative of u is 1. The integral of e to the power negative x is negative e to the power negative x. Because you notice it's going to keep on changing. Only thing that's going to change is the coefficient from positive 1, negative 1 on the integrals of v. So once we have these, we could plug them in there. We have x times negative e to the power negative x from 0 to 4 minus the integral from 0 to 4 of negative e to the negative x times 1 dx. Let's go and wait till the end and do all these at one time. So I have negative x e to the power negative x from 0 to 4. The integral of that negative changes to a plus. So the integral of e to the power negative x becomes negative e to the power negative x from 0 to 4. So now we just look at each one of these separately. So negative 4 e to the negative 4 minus negative 0 e to the power negative 0 plus that's going to be minus again. E to the power negative 4 minus e to the power negative 0. You got negative 4 e to the negative 4. That disappears. Minus e to the negative 4 plus e to the 0. Negative 4 e to the negative 4 minus e to the negative 4 plus 1, which is negative 5 e to the negative 4 plus 1. And whatever those numbers are, when you plug them in the calculator, will be your answer. right, well, that does it for that one. Any questions? I'm sorry I went pretty quick, but I mean, it's always the same process. Once you find the u and v prime, it's just a matter of doing the derivative of one, integral of the other, and just plug and play in the formula. I'm not gonna lie to you, there are gonna be times where you may have to do it 2 or 3 times on some part of it. You might have to do integration by parts a couple of times. But once you get the integration by parts, the repetitive part, so it looks like the original question, stop there, move it over, and once you solve for that, you're done. Once you get the final step looking like the original equation, you're done. Whatever's on the right-hand side is the answer. Any questions? Anybody still awake? Just kidding.
I'm awake.
No, my first class started at 8 o'clock, which was 3 o'clock over here. So
Oh,
yeah, I woke up at 2, get everything ready, and it's right now 6 o'clock. So
6
I'm
p.m. or 6 a.m.?
AM.
A.m.? Oh,
Yeah, it's not gonna change to PM until I get to Tokyo and that part of the world, because then they're 14, 16 hours behind.
ew. I'm so sorry. Oh no.
But it's worth it. I mean, it's on a bucket list. You just have to make it a trip out here to this part of the world eventually, because